In this section, I'd like to explain the Laplace equations. We encountered Laplace equation in many areas such as electrostatic, gravitational, and velocity in fluid dynamics. Also, this equation is very important to describe the steady-state temperature distributions. So in the case of steady-state temperature distributions, U corresponds to the temperatures. To describe temperature distributions, we use a linear second-order partial differential equation. Because of the steady state, U is not a function of the times. Instead, U is a function of the space coordinate. So second derivative of U with respect to x plus second derivative of U with respect to y equals 0. This is a differential equation we consider. As a boundary condition, at x equals 0 and x equals a, no heat flow, so insulated boundary condition we apply. At y equals 0, temperature is constant 0. At the boundary y equals b, temperature distribution is described by the f as a function of x. So we applied this boundary condition to solve the differential equations, Laplace equations. Again, we use a separation of variables method to solve the Laplace equation. We consider that U is a function of the capital X and capital Y. And capital X is a function of the X, and capital Y is a function of Y. And substitute into the partial differential equation. Then second derivative U with respect to x becomes x2 primes y. Second derivative U with respect to y is x y2 primes. We substitute this expression into the Laplace equation. Then we obtain this equation. x2 prime over x equal minus y2 prime over y. So right hand side is a function of the y alone. And the left hand side is a function of the x alone. To satisfy this equation has to become the constant value. As a constant values, we choose the minus lambda. Then from the single equation, we derived two equations for the capital X and the capital Y. By considering the boundary condition at the x equals 0 and x equals a, derivative of the capital X with respect to x becomes 0. So we use this boundary condition. By applying this boundary condition, we find out the solutions for the capital X. When the lambda equals 0, x becomes a constant value of the C sub 1. And also to satisfy the boundary conditions, we discover the other eigenvalue of the lambda. Lambda is expressed in this equation. Lambda is n pi over a squared. Capital X is expressed C sub 1 times cosine n pi over ax. We find out the solution for the capital X. We applied another boundary condition for the y. At the y equals 0, u becomes a 0. So u x0 equals 0. So this means x, capital X, x, y at a 0 equals 0. So from these equations, y0 equals 0. So we applied this boundary condition to find out the expression for the capital Y. We use the equation for the capital Y. And if you consider the lambda equals 0, you can easily solve for the capital Y is a C sub 3 plus C sub 4 Y. If you apply the boundary condition at the y0 equals 0, you can find the C sub 3 equals 0. Then as a y is expressed as C sub 4 times y. When the lambda equals n pi over a squares, the general solution for the capital Y is expressed C sub 3 hyperbolic cosine n pi over ay plus C sub 4 hyperbolic sine n pi over ay. Then we apply the boundary condition. Capital Y becomes 0 at y equals 0. You can find that C sub 3 becomes 0. So as a solution of the capital Y is expressed C sub 4 hyperbolic sine n pi over ay. The solution of the Laplace equation, when the lambda equals 0, is corresponds to n equals 0, the u sub 0 is expressed a sub 0 y. When the lambda is n pi over a squares, is n is take an integer 1, 2, 3. The solution of the u sub n is a product of the capital X, capital Y is expressed a sub n hyperbolic sine n pi over ay times cosine n pi over ax. So general solution u as a function of x, y is a sub 0 y. This corresponds to the n equals 0 plus sigma n start from the 1 to the infinity a sub n hyperbolic sine n pi over ay cosine n pi over ax. Then we need to determine the a sub 0 and a sub n. Then we apply the last boundary condition. So you can substitute y equal b. The boundary condition is given fx. And the a sub 0 and the a sub n we need to determine. By integrate both sides of the equation from the 0 to the a, you can find the a sub 0. Then by multiplying the cosine m pi over ax in the both sides of the equations, you can find the a sub n. We use the same method to determine the a sub n in the wave equation and the heat equations. Once we discover the a sub 0, a sub n solution for the Laplace equation is expressed this. Then I'd like to show you some numerical results. In these cases, we consider u is a fixed values of the 100. Y equal 1, constant temperature is given. This is u equal 100. U becomes a 0 at a y equal 0. So this is a constant values. Then we'd like to find out the steady state temperature distribution. So this is a solution. To find out the exact solution, we have to take into account the infinite number of terms. But it's impossible to take into account the infinite number of terms. Instead, we consider the 100 terms to draw these figures. Sometimes it's quite difficult to find the temperature distribution in a 3D surface. Instead, sometimes we draw the isotherms. So this corresponds to the 100, u equal 100. This corresponds to the u equal 0. And this is the isotherm for the u equal 10, 20, 30, 40, 50, 60, 70, 80, 90. So in this section, I explained how to solve the Laplace equations. Okay, this is the end of this session.